All right, so this is exam 3.2. I'm going to move through this as briskly as possible. The first question reads, if these four metals were added to a pot of boiling water, which would reach 100 degrees fastest, considering their different specific heat capacities? So the correct answer to this is the metal that has lowest specific heat capacity, because that's going to most easily change temperature based on the amount of heat added. Question number 2, a 50-gram piece of gold has a heat capacity of 100 or 0.129 joules per gram degree Celsius. If you supply 300 joules of heat to that gold, what will be the change in temperature? And so to get this question, what we basically need to do is we need to take that 0.129, multiply it by 50. 0.129 times 50. And so that gives us, well, for every 6 degrees, or sorry, 6.45 joules of heat, we'll see 1 degree of temperature change. So then we take 300 and divide it by 6.45. And you end up with 46.5, or answer option A is the correct answer option for this. So I'm filling out my key while I do this. This is C and A. Question number 3, for a chemical reaction that occurs under constant pressure conditions, if the change of the enthalpy is positive, which of the following statements is true? If the enthalpy change is positive, the reaction is endothermic and the heat is absorbed from the surroundings. So C is our correct answer. Question number 4 reads, a 25-gram sample of an unknown metal is heated to 35 degrees Celsius and then submerged in 200 grams of water at 25 degrees Celsius. The final temperature of the system is 32 degrees Celsius. What is the specific heat capacity of the unknown metal? Okay, so for this question, what we would want to do is we want to take, I'm going to go ahead and show this on the whiteboard, show the math for this one. What we will do is we will see Q metal is equal to negative Q water. This is the same as MC delta T is equal to negative MC delta T. Okay, so the mass of our metal is 25. The specific heat capacity is what we don't know. So I'm going to put an X there. Our delta T, well, we have that metal that's heated to 35 degrees Celsius, and then its final temperature is 32 degrees Celsius. So 32 minus 35. 25. Then I'm going to put that in parentheses. And then I'm going to put X in parentheses. My delta T is 3. So this is effectively 75. X is equal to negative mass over water, which is 200. Specific heat capacity of water is 4.184. And then our change in temperature is, well, it goes from 25 to 35 to 32, so that's 7. So plug this in my calculator, which I have one on my desk. I assume I don't, so I'll use my computer calculator. And I see 200 times 4.184 times 7, and I get 75x equals, no, actually, sorry, this is a negative 3, so that's negative 75x. Negative 75x is equal to negative 5857.6 divided by negative 75. X is equal to negative 5875 divided by negative 75. And the correct answer is X is equal to 78.1 joules per gram degree Celsius. Okay, now let's look back at our answer options to see which one fits best. And upon close inspection of our answer options, 78 is not one of our answer options. So for this one, I'm going to leave this one blank and award everyone credit for this. I really apologize for that. That was bad form. Question number 5 reads, consider a gas in a piston cylinder system. During a certain process, the gas releases 900 joules of heat from a heat source and performs 600 joules of work on the surroundings. What is the net energy change? So this is releasing heat and it's doing work. So those two things are both leaving the system. So D, negative 1500, is our correct answer. Number 6, consider the reactions shown below. What we have is a series of reactions where we have our overall reaction and then these 3 reactions that we need to manipulate to match up with that. The one thing that I notice about this is we've got carbon as a reactant and carbon as a reactant. We got to get rid of that carbon. So what we're going to do is we're going to take this reaction right here and we're going to flip it around. And so the delta H for that is going to be 74.8. Okay, then this last reaction, we've got to multiply that by 2. So that's going to be negative 285.2 or 0.8 times 2. So 285.8 times 2, it's going to be a negative value, plus negative 393.5 plus 74.8. And that gets us our correct answer, A, negative 890.3. So that's 6A. Okay, number 7, for a chemical reaction that can be expressed as a sum of 2 or more step reactions, which of the following statements is about Hess's law is correct? Ultimately, C is correct. Hess's law allows us to determine the enthalpy change of the overall reaction based on the enthalpy changes of our step reactions. That's basically our definition for Hess's law. For the reaction 2SO2 plus O2 yields 2SO3 with an enthalpy change of negative 197.8. How much heat is absorbed or released when 8 moles of SO2 react to form sulfur trioxide? Okay, so we have 8 moles of SO2. Our balanced chemical reaction shows us 2 moles of SO2. So what we need to do is we need to take this 197.8, simply multiply it by 4. 197.8 times 4, that is 790, negative 791. So B is our correct answer for number 8. I need to scroll up so you can see. Okay. Question number 9. This one reads, if the enthalpy change for a reaction is negative 484 kilojoules, how much heat is released when 4 moles of H2 gas react to form H2O? So this is just taking this value right here, this 2 moles of H2, and saying, well, what if there's 4 moles of H2? So that means we need to take this number and multiply it by 2. Negative 484, well, that is going to be B, 968. Okay, number 10. What is the pressure of gas in atmospheres if it measures 1044 millimeters mercury? Okay, so you need to know the conversion. 1 atmosphere is equal to 760 millimeters mercury. And that's almost that 1044 is almost 2 times. It's almost 1.5 times 760. So our best answer option is B, 1.37 atmospheres. That's number 10. Number 11, the container contains a gas with a pressure of 2.5 atmospheres. What is that pressure in torr? Well, 2.5 times 760 is 1900. Number 12, a sample of gas that occupies 3.8 liters at a pressure of 9.3 atmospheres. If the volume is reduced to 2 liters, what will the new pressure be? Okay, assuming that the temperature remains constant. So we could think about this kind of logically. Our volume is going to decrease. What's going to happen to our pressure? Okay, so basically we have a gas and then we shrink the container down. Well, do we think that our pressure is going to be 4.9 or 5.39 atmospheres? No, those are both unattractive, bad answers. Then A and D. Okay, well, this 17.7 shows that our pressure nearly doubles. And then D shows that it goes up radically. Now, if you wanted to approach this and do the math for it, you'd see that the correct answer is A, because our equation for this would be P1V1 equals P2V2. So our pressure, 9.3 times 3.8. 9.3 times 3.8 is 35.4. And then divide that by 2, and you get 17.7. So the correct answer for number 12 is A, 17.7 atmospheres. Okay, the question above can best be explained with Avogadro's, Vespucci's, Incaviglia's theorem, Boyle's law, or Charles's law. The correct answer for this is Boyle's law. I always was told you're dealing with P's and B's, peas and vegetables. You're boiling those on the table. PV over T equals PV over T. So you boil peas, like the vegetable, and the other vegetables. So 13 is D, Boyle's law. Number 14, if the temperature of a gas is increased while keeping the pressure constant, what happens to the volume? Okay, so we've got this enclosed container, and we heat it up. Now we keep the constant pressure, so the pressure constant, so what's going to happen to the volume? The volume is going to increase. And C is the only answer option that indicates an increase in volume. The others are it's cut in half by a certain amount, it doesn't change, or you can't figure it out. So 14 is C. Number 15 reads, the question immediately above is best explained with, and this one is going to be Charles's law. So 15 is A. 16 reads, a gas occupies a volume of 6.5 liters at a certain temperature and pressure. If the temperature and pressure remain constant, what will the new volume, if the number of gas molecules is doubled? Okay, so the temperature and pressure remain constant. Avogadro's law says that we're going to double the volume. So 16 is C. A gas sample occupies 9 liters at 25 degrees Celsius, 1 atmosphere. If the pressure is increased to 2 atmospheres and the temperature is changed to 0 degrees Celsius, what will the volume of the gas be? Okay, so we've got a couple of answers. 4.12, negative 13.6, a negative value. E cannot be determined. B is out. You can't have a negative volume. D is therefore out for the same reason. And E, also not a very good answer, because can this be determined? Absolutely. So this is PV over T is equal to PV over T. So 9 liters are volume, 9 times 1 is our pressure, divided by our temperature, which is 298, because we have to convert our temperature from 25 degrees Celsius to Kelvin. So that gets us a number of 0.0302 and so on. Now, what we're going to do with that is we're going to increase our pressure from 1 to 2 atmospheres. Then our temperature is going to go to 273. So what we've got here is we're going to multiply this by 273.15, and then we're going to divide this by 2, and we're going to end up with A, 4.12 liters. So just to show kind of, okay, so there we go. So 17 is A. Now, number 18, a gas sample with a volume of 2 liters at 25 degrees Celsius and 2 atmospheres. What's the number of moles of this gas? Okay, so this question is really at its heart. This is an ideal gas law equation. You have a pressure, 2 atmospheres. You have a volume, 2 liters. You have a temperature, 25 degrees Celsius. You also have an R value that we haven't even really gotten into there. So what we can do is we can plug all this in and say, calculator, So we can take the ideal gas equation, PV equals nRT, and say pressure 2 times our volume 2. And then divide that by R and T. Our temperature is 25 plus 273 or 298. So I'm going to say divide by 298.15 times my gas constant, which is 0.08206. I can close my parentheses. And my answer is going to be 0.1634, which if I look at my answer options on my test, we got point. Oh, the answer option C is my best answer option. So 18 is C. Number 19, 5 moles of a gas occupies a volume of 5 liters at negative 10 degrees Celsius. What is the pressure of this gas in that container? Okay, so in this case, this is another ideal gas flow equation. So I have the pressure, or I don't have the pressure. I'm sorry, that's what I'm solving for. So I'm going to take my equation, which I'm going to say PV equals nRT, and I'm going to rearrange it so that I basically am just saying nRT divided by my volume. Do I have my n? Yeah, it's 5. So 5 times 0.08206 times 263.15 divided by 5. And I get 21.6 out of atmospheres. So there we go for that one. Number 20. What units must temperature be measured in? Kelvin. According to the ideal gas law, what happens to the volume of a gas if the pressure and temperature are held constant while the number of gas particles is doubled? Okay, our number of gas particles are doubled. What that means is that the volume is also going to double. Okay, so that wraps up 3.2. I hope this is helpful, and I hope this is good review for this content. All right, well, have a good